Okay, so I'm glad to introduce Professor Aslan Tchamkerten, who is a professor in Telecom Paris. So Aslan is information theorist, interested in many very beautiful topics. We met first in Berkeley, I think, by chance. So we had never met before, and I'm very glad that he accepted our invitation to lecture on data compression with locality. So Aslan is in another department, not informatique et réseau. It's Comelec, and there are several colleagues here with whom we should interact more. And so I'm very glad he accepted our invitation, and hope this will lead to further interaction. Aslan.
Thank you, François, for the introduction. So, I mean, I have no idea about the general background. So, the talk is, I can modulate the talk, as we want. So, do all of you have some background in information theory or some not that much? I mean, yeah, basics, okay? Basics, okay. Well, all right, so great. Okay. What? You don't meet information. Okay, actually, I'm going to stick with entropy. So, boom. All right. So this is but what I'm going to present is based on a joint work with, actually a sequence of joint works with Shashank Fatetka, who is a former, now a professor at IIT Hyderabad, as a former postdoc, and Venkat Chander, whom I met in the old days when I was at MIT, and he was, I was a postdoc, and he was a PhD student, and ever since, he has a lot of free time at the Shaw to continue to work with me. So this is great. Okay, so oops. So let's start by a short presentation on data compression. Okay, so compression is all about taking a source of information, which I'm going to refer to as xn, x superscript n, and compression is all about reducing the size of a source file, right? So we want to encode xn to a certain number of bits. I'm writing it as nr, and so nr is a size of your archive. So I'm referring to it as CNR. So CNR is the encoding of the source sequence xn, and traditionally, I mean xn, for model purposes, is supposed to be IID distributed according to some underlying known distribution Px. Okay, and throughout the presentation, Px will be defined over a finite alphabet. Okay, I mean, think of it. If you want to just, I mean, most of the talk will be valid for. I mean, what I'm going to say is mostly valid for Bernoulli, for binary sources, and are tiny extensions which you can make if you want to have general alphabet. But I'm just going to skip this under the rug. Okay, that's not really. I mean, just tiny technicalities. So for our purpose, xn is a binary sequence. We compress it to nr other bits, and of course we want good reconstruction, right? We don't want to have any distortion between we don't want the compression to result in any loss. So we want the reconstruction that we get from the compressed archive to be essentially more or less without error. Okay, so without error, I mean that the probability that x hat n differs from xn should be little o of 1, and this little o of 1 is as n tends to infinity. Okay, just all right. So Shannon in the 40s showed that the minimum R for which you can guarantee reliable reconstruction is the entropy, h of x, okay? And so how do we prove this? So it's very simple. So we take n long, we have a long file, and we can just apply law of large numbers, okay? So basically, we know that if n is large, the empirical frequency, the number of times they're going to see any symbol x is more or less equal to to the true, to the probability of that symbol. And so you can just now consider only the sequences that have this typical behavior, okay? And so how many of those are there? I mean, there are about 2 to the n h such sequences. And the good thing is that this set of sequences is a high probability set, okay? So you can just ignore all the others and you restrict yourself only, and you compress only, I mean, you represent only those typical sequences, okay? That's it. And what you get is you get arbitrarily close to entropy, and the probability of error will be exponentially decaying with n. Okay. Okay. So this is to show that any r above h of x is achievable. Anyway, essentially, a similar argument can show that you cannot go below h of x. Okay. All right. So this is all about data compression. Now, if you pick any of our, if you consider any compressor that is available, like Lempel-Zip, for example, which is available, which is implemented in Xip, for example, it is non-locally decodable, non-locally encodable, and non-locally private. Okay, so what does that mean? It means that if I want to recover a source symbol xi, right? In general, I have to read the entire archive. Okay, the compressed archive. Similarly, if I have my original phi xn, I just do an update of a single symbol. In general, this results in a complete change of the archive. Okay, and finally, it is also non-locally private in the sense that if you want to recover any xi, okay, well, because essentially you have to decompress the whole thing, you cannot do it privately. Okay, you're going to discover also, I mean, essentially you're going to know lots of things about other symbols and potentially all of them. Okay, so we're going to address those problems. Okay, the central problem here that we're going to talk about is, can we design compression schemes that are efficient in the compression rate, but which are also local in some sense? Okay. All right, so this is in this presentation, I'm going to talk about limits to compression with local decoding for a single source. Then we're going to see that if we move to multi-user compression, there's a big difference between the two situations. And I'm going to talk about compression with private local decoding. Okay. All right. Compression with local decoding. So here is the setup. We have, so we encode a source sequence xn to code word CNR, same as before. But now, instead of having one global decoding map, which takes the archive and produces the original source file, we have n local decoders. Okay, those are referred to as x hat I. Okay, so x hat I is the decoder for the ith source symbol. Okay, so xi hat takes as an argument CII. So CII is a subset of code word symbols. Is a subset of code word symbols that I need to read in order to decode symbol I. Okay.
They're contiguous.
Pardon me?
They are contiguous.
What is not necessarily? Not necessarily. It can be anything. And this is completely. So this is basically how I define things. Then I have, of course, to see that such things exist. Okay. So now I'm just defining what the local decoder is. The local decoder need not query things, bits that are contiguous. Yeah. All right. So now again, the decoder is composed of n local decoders. Okay, one for each symbol, and for each symbol there is potentially a different set of code word symbol that I need to query in order to identify the value of the corresponding symbol. Okay. All right. Now I'm going to define locality. So II again is a subset. I mean, is the positions of the code word symbols. Actually, there should be should be not n, but should be nr, right? Because I'm just reading from the archive. Yeah. So II is a subset of positions that I'm reading, from the archive to recover symbol I. Now, the way I'm going to define locality will simply be, the worst case, right? So the maximum number of, I'm looking at all the sets of symbols that I need to query to read, to reconstruct the corresponding symbols. And, I'm taking, largest value defines locality. Okay? Is this clear? Yeah. So this is for locality. And then I'm going to define the local error probability as, for each source symbol, there is a reconstruction error, a local reconstruction error. I'm going to consider the maximum of those, and this defines the local error probability. Okay, so worst case in the local probability, in the local probability of error, and in terms of the number of bits that I'm reading. Okay. Okay. So now comes a problem. So given a target compression rate, how small can you make L?
L can depend on N or not?
Potentially, yes. Potentially, yes. Okay. So ideally, we want to have L as small as possible. Oh, one thing. Yeah, sorry. So we want to minimize L among all compression schemes. And again, compression scheme is an encoding procedure and N local decoders, right? So among all compression schemes that have this property, so the local error probability should decay as little o of 1 over n. And why little o of 1 over n? Simply because if we have little o of 1 over n, then we can also use all the local decoders to derive a global decoder that will produce the whole sequence reliably, right? Just by union bound, right? Yeah. Okay. So and you have a little picture on the right there. For example, if you want the local decoder for symbol 2, queries symbols 2 and 3, and you get your estimate. Okay, and you have n such boxes, one for each source symbol. Okay, so let's start with a baseline solution. Okay, so if you don't know anything about locality, basic, a very simple solution is just to chunk your data set. Okay, so you take your data set of size n, you decompose into blocks of size b, okay, and you compress each block at the desired rate r, and that's it. Okay. Decoding, very easy. You just decode the symbol, the block that corresponds to the symbol that you are querying. Okay. So the maximum number of bits that you are actually querying is by definition the size of the chunk. Yeah, simple. Okay. So in terms of performance, the error probability, well, it is tied to the size of the chunk, right? So essentially e to the minus, is exponentially decreasing in the size of the chunk. Okay. So if you want now the probability, the local error probability to decrease as little o of 1 over n, then L has to grow with n. Okay. There's no other possibility. Okay. So this is a baseline solution. So we know that some level of locality is possible. Okay. So go from n to log n. Okay. Good. Can we do better? Okay. So a priori may seem hard, right? But amazing, yes.
So it is a big omega of log n, but then can we reach this value? Because if I remember well, omega, the ratio of omega,
yeah,
means that it is bounded by the constant times log n.
It's as long as you take L, which is some constant times log n, that's it. You get the answer. Yes.
But, if I remember well, the big omega means that you have a lower bound on the L.
Yes.
But it doesn't mean that the lower bound will be proportional to you
can. So maybe okay. So it depends. Okay, if you have this, then L is true. Then it depends. How much you insist on the decrease, right? So if you want to have if you want the probability, the only thing that you have
yeah, okay.
Right. I mean, you can trade, L with the error probability, right? So if you want smaller probability, you have L. L has to increase. Okay. So, I'm going to present, an optimal solution. An optimal solution is basically essentially showing you that we can get exactly the same thing, but by essentially with constant locality. So constant locality here, and a local error probability which is exponentially decaying in n. Okay. So yeah. So again, so how do we move? So how do we go from locality log n to constant? So what I'm going to present here is based. I mean, this is all work from essentially about 10 years ago, and so here's the idea. So the main tools are ray distortion and a very, very nice data structure result by Berman, okay, from 2000. So let me state this result, okay, because it's a really, really neat result. What Berman showed is that there exists a locally decodable compression scheme for epsilon n sparse sequences Sn, such that blah, okay? So let's pause here, okay? What does that mean? It means so epsilon n sparse sequences are sequences which have at most epsilon n ones, okay? So binary sequence at most epsilon n ones, okay? So it's a very restricted set of sequences, okay? Mostly zeros and a few ones here and there, okay? There is no distribution on this set, okay? And what he showed is that if you have this set of sequences, epsilon is known, then you can compress that set to an archive of size of length n epsilon log 1 over epsilon. Okay, this is one thing. The other thing is that you can also retrieve any source symbol with at most, log 1 over epsilon bit probes. Constant number, that's the point. Okay, constant number. Okay. So what is the compression rate that you get here? The compression rate is epsilon log 1 over epsilon. Okay. So how good is this? I mean, at least we get some compression there, right? We have a nice, I mean, this is the first result about non-trivial result about local data, data compression with locality, right? So how good is this rate of epsilon log 1 over epsilon? It's pretty good. It's very close to entropy. It's order-wise, it's same as entropy, right? Epsilon, the entropy would be epsilon log 1 over epsilon plus 1 minus epsilon log 1 minus epsilon. So 1 over 1 minus epsilon, okay? Yeah, so in the limit of when epsilon goes to 0, order-wise, it's the same. Of course, there is a big O here, right? There's a constant, but order-wise, it matches entropy. Okay. Okay. So the whole problem now is how do we lift this result, which is valid for very, very sparse sequences, to IID sequences of with some distribution, right? So here's the idea. We're going to do. We start by chunking the original data set, okay? So this is exactly the same as in the naive setup, right? So we take Xn, we decompose it into blocks, but now the blocks is of constant size, B, okay? Constant size. Now, if you do this, because B is constant, there will be errors, right? B is not log n, there will be errors. Some find, the probability of having an error in any block is some constant. Of course, you can make the constant as small as you want, but it will not decrease with n, okay? Yeah? Okay, so this is for Xn, right? X hat n represents the reconstruction that we have for each of the blocks, right? And now, En, what is En? So En is the error vector, right? So you have xn, x hat n. You compare the two, you have the error vector. And the beauty now is this error vector is sparse, okay? Right, so there are very few positions where actually you'll have where you'll have errors, right? So the overall error vector has at most, if the error per block is epsilon, the overall error vector has at most, 2 to the n epsilon b errors with high probability, and then you can just compress that, okay? You can use the previous result, and instead of compressing, the source sequence, we can actually compress the error sequence, okay? And that's it. So now how do we decode? We decompress the corresponding block, right? You get x hat for a particular block, and then what you do, you want to retrieve a particular xi, right? And then what you only need to do is to find the possible the error symbol for that particular x hat I, right? And this is how you get xn, right? Okay, so the locality will be, well, the size of B, which is constant, some constant, plus the number of queries that you need to make in order to identify the error symbol. Yes?
So I didn't understand if this is still lossless or not.
So it's a good question. So there is the only error will be because of the because of the errors that you make in the original. So what I'm doing here, look, overall error vector has at most 2 to the n epsilon with high probability. So there might be situations where xn actually produces more errors. Those, you'll have, there will be errors, okay? But if you are as long as your xn has, provides, resulting at most 2 to the n at 2n epsilon errors, you're good, right? Because you are within the bound of the error vector. Yes?
When you compress the error vector, you are not local. Like the compression, I got the locality of the compression of X, but I
well, yes, but locality doesn't mean that they have to be together, right? Locality means that you want to, maybe locality means that the number of symbols that you want to query should be small. And in fact, here they can be completely scattered across, right? Once you compress the error vector, right, you get an archive for the error vector, right? Just pieces of it, exactly. Yes. Yeah, yes.
For the decompression, we need that chunk of the
you need a chunk?
And also the whole error, right?
Not the whole error, only the few bits from the compressed error vector that you need to recover EI.
Yeah, but I mean, the indexes shouldn't necessarily be in the
no, not at all. They can be. They could be. Yes. It's a different file, right? So you have decxn, decompose into blocks. You map. You compress each little block, and then you have the error vector. You have a separate archive, right? So to decode any particular xi, you're going to read the corresponding, decode the corresponding block, and then read the few symbols from the compressed error vector.
Just another
Sure.
question, to compare with the simple chunking.
Yes.
The simple chunking compression, you do not need an error vector. So
there is no error vector.
there's
Yeah.
no error vector.
Yes.
So basically, you get that compression factor without the additional space required to store the.
But it's very small. It's really small. Yes. And this very small amount of information that you're provided, this is what helps everything, right? You get an exponential decay in terms of error probability. Exactly. Yes.
sorry.
Yeah.
reminiscent of compressed sensing.
It is reminiscent. It is reminiscent. It is not, I mean, okay, one thing I should mention is that the result by Berman is not explicit. So it's an existential, yeah, it is existential. So the compression algorithm that, that he shows, for which he shows the existence, it doesn't exist. I mean, it doesn't exist. It exists in probability, okay? Now, it is reminiscent. I see what you're saying. I mean, it is reminiscent in the sense that it goes, I mean, compressed sensing is all about, you basically leverage on the sparsity of the vectors you want to reconstruct. True. But it was really, I mean, I don't see, I mean, data compressed sensing is not about, compression. There is no notion of encoding a vector into a smallest, maybe.
Yeah, but there is the concept of random coding decoded vector, which has the same.
Yes, yes, yeah, okay, I agree. Okay, maybe. Okay.
Yeah, yeah, I think.
Okay. Well, okay. So as a summary, here's for a single source, the baseline scheme, we achieve what I'm referring to as weak locality. So error probability decreases as as exponentially in locality, and strong locality is basically you decouple L with the error probability. Okay, so this is what happens, and you can get constant locality and nevertheless getting a local error probability, which is exponentially decaying into big block. Okay, in N. Okay, so since I have so I was thinking. So there are three parts. I was thinking to show you the extension to the multi-user setup. But what I was saying, I mean, what I'm going to do, I'm just give you the result, and I'm going to talk to something which is hopefully much more tangible. So in the distributed, so here's the distributed, it's the same problem as before, except that now we have two sources, Xn and Yn. Okay, so this is set up as referred to as the Slepian-Wolf problem. Okay, two sources separately encoded. We provide the two archives CNR1 Xn and CNR2 Yn to the decoder, and the goal of the decoder is to reconstruct Xn and Yn reliably. Okay, so this is Slepian-Wolf, and the problem is, okay, can we say something about locality? Okay, so let's yeah, so so we define things exactly the same in exactly the same way as before. So for each position I between 1 and n, there is a set of probe locations at the receiver. So now the receiver gets two archives, one that comes from X, and the other one that comes from Y, right? And II represents the union of all the positions that I'm querying either from user 1 or from user 2. Okay, and then we can ask, what type of locality can we get? Okay. So it turns out, and here's what I'm going to skip this. So it turns out that in most cases, when you have this multi-user scenario, strong locality is impossible. Okay, so there is something in this multi-user setup that prevents strong locality to happen. Okay. Okay. So I'm going to maybe, I mean, if I have time at the end, I'm going to come back to the proof of this, but so it's a bit long. And all right. So let me immediately jump to the third part. Okay. So this is a so I like this problem. And this is a problem that basically took us like essentially 2 years to solve. And we initially thought was possible, then no, and yes, and no, and more. So here's the problem. So we have a source xn, we encoded, and now what we want a local decoder for a particular symbol, see here too, and this local decoder should reveal no information about the other symbols. Okay? So in other words, so in this case, reading C2 and C3 should provide information only about X2 and nothing about the rest. Okay? So if you think about it, I mean, our first intuition at least was this, I mean, how can you do, right? You start with a xn, you compress it, but so intuitively we mix everything, right? So we add dependencies because otherwise you would not be able to compress, right? So it turns out that this intuition is completely wrong. Okay. Okay. So here's the result I'm going to present. So any ID source of information is compressible to the entropy rate with perfect private local decoding. Okay. So not only you can compress, but there is no rate loss. So maybe we could compress up to say 2 times entropy, but no, you can go. There is no penalty in terms of compression rate. So and the algorithm, the compression algorithm, is extremely simple. Okay, so so suppose first that xn is drawn uniformly among all sequences with the same empirical type. Okay, so fix a distribution. Okay, and you consider compatible with length n sequences. Okay, take a random permutation, and this is the output, and this is what the source will produce. Okay, yeah. So xn, constant composition. Now, the first thing to do is to simply apply a random permutation to all the symbols. Okay, apply a random permutation, and then you compress the shuffled version. You don't compress xn, but you compress x tilde, right? So x tilde is just the shuffled version of your original file. Okay. So we compress the permuted version, we get an archive. This is part of what I'm what I'm going to reveal to the local decoder. So the local decoder gets to see now CNR and sigma I. Okay, and that's it. Okay, so sigma I is it's just a result of the permutation on the symbol, on the ith symbol. Okay, so if you get this now, so this is what the local decoder for symbol I gets to see, and what the local decoder will do gets this. It will you get this. It will decompress and get the shuffled version entirely. And now this sequence x hat n. I mean, the decoder doesn't learn anything. Basically, what is that? What does it observe? It observes a random sequence, which it knows is of constant composition, right? So there's absolutely no information there, right? And then with the addition of sigma I, you get what you want. Okay. So perfect privacy. Okay. There's one problem here, is the compression rate. How much do we need to store? Where do we store? We're storing NR, okay, NR bits for the shuffled archive, but then we also need to store the permutation, right? So essentially n to the n possible permutation, n log n bits. Okay, terrible compression rate. So how do we do? So there is a very easy fix to this. We decompose xn into consecutive blocks of size b, okay, small blocks, and then we apply the same permutation on each block to amortize the cost of this big permutation. Okay, okay, and now the compression rate will be nr, again, nr bits for the compressed shuffled source. And this n log n becomes log n log n, which is essentially R. Okay, that's it. So far, we can get entropy rate compression with perfect privacy if the source is composed of blocks of constant composition, right? This whole thing relies on the property of constant composition, because when I open CNR, right, I don't learn anything. I'm observing a random sequence from a constant composition distribution, and this doesn't change. Okay, it's always that. Okay, okay. So how do we do for an IID source? Well, we're going to add a little step at the beginning. We're going to make the source constant composition. Okay. So here's one thing that could go wrong, right? If we just apply blindly exactly the same, we just apply the same compression algorithm on IID source, what could happen? Well, the source, for example, imagine I have a Bernoulli P source. If my source is now, if I observe the whole zero sequence, or the whole zero sequence with a few ones, when I see this, right, I can guess a lot about the other positions, right? That's why I need constant composition. But making an IID source constant composition is it's very simple, and it results in a tiny penalty. Okay, so how do we do? So we know that with high probability, the number of occurrences of symbol X in B, is at most B times PX plus epsilon. It's just large deviations. And so what we can do is that you can just add symbols so that the number of occurrences for any symbol X is exactly B times PXX plus epsilon. Okay. So we marginally change the distributions, not much, by adding very few symbols, right? And then we use the permute and compress algorithm that we saw before, right? Now we have perfect privacy and entropy compression rate. Okay. And again, since padding modifies, because now we are not compressing the original source, we are compressing the padded sequence, the shuffled padded sequence. Okay. Okay. So yeah. So again, so so how should I do? So either you could stop in a few minutes, or I can go but I would need 15 minutes to at least cover some of it's as you wish.
We have time.
We have time? Okay. So let's go to the proof. Yeah, let's go to the locality in distributed compression, right? So again, you have two users, two archives, and then we have for each index I between 1 and n, we have a local decoder, and then the local decoder needs to produce an estimate of the corresponding source symbols. Okay, and one thing which I forgot to mention here is that xn and yn, they are correlated over space. They are not necessarily independent, but they are independent across time. Okay, so there's a probability of xn comma yn is a product distribution across time of pxy. Okay. Okay. Baseline solution can just do exactly the same thing as in for the single user case, and you can immediately see that locality, we can easily achieve weak locality. Okay. Again, can we do better? And the answer is, as alluded to before, the answer is no. Okay. But a few more details here is that the answer will depend, of course, on the rates at which we are operating. Okay. So for example, if you operate at R1 greater than h of x and R2 greater than h of y, well, then you can certainly achieve strong locality, right? So the two users will just completely ignore the dependency between x and y, if any, okay? And just compress at the desired rate because I mean, there is sufficiently slack above h of x anyway, so you can achieve strong locality. Okay, so you can just duplicate the single user case in this regime. Okay, so it's not very interesting. The interesting problem is if either R1 or R2 is less than the corresponding entropy. Okay, can you get strong locality if either R1 is less than h of x or R2 less than h of y? Okay. And the answer is no. Strong locality is not possible unless the source is very specific. So what does very specific mean? So here's an example of a very specific source. So suppose x and y, so the joint distribution of x and y is given by, the marginal of x is a Bernoulli parameter alpha, and when we pass this x across a channel to get y, okay? Okay, so this picture on the right indicates the conditional probability of observing, E, for example, given 0, E given 1, 1 given 1, and 0 given 0. Okay, this represents the conditional probabilities. Okay. Okay. So if we are in this setup, if this is the source distribution, then what can we do? So the thing to observe is that we, as the Y user, we don't need to send information that discriminates between 0 and 1. Okay, why? Because if y is either equal to 0 or 1, there is no ambiguity. Okay, because of x. Okay, so we can completely give the work to x, and x will help the decoder identify whether y was equal to 0 or y was equal to 1. Okay, so one idea here is that instead of compressing, to what the y user will do, it will map y into the random variable z, which simply ignores the 0 and the 1, does not distinguish between the two. Okay, so one symbol for either 0 or 1, and another symbol for symbol E. Okay, that's it. So then you can easily see that x and y provide as much information as x and z. Okay, you can go back and forth. There's a bijection. Okay, but now the nice thing is that h of z is less than h of y. Okay, so therefore we can achieve R1 equal to h of x. So the x user will compress, ignoring the other user by operating arbitrarily close to its entropy, but the y user can save something. Okay, can communicate, in particular, can transmit at a rate below h of y. Okay, but it's a very specific example. Okay, so in a nutshell, the BSC example illustrates what you can do if distribution is kind of strange. Okay, so now let's define what a notion of confusability. We're going to say that P of xy on x, y is said to be x confusable if for any distinct x on x prime, there always exists a y which can confuse them. Okay. So for example, if you go back to the BEC example, we see that the joint distribution is x confusable because there are just two inputs, and then there is a y which confuses the two symbols on the left, right? But it is not y confusable, right? It is not confusable because, for example, those two, there is no symbol here that can confuse those two symbols. Yeah. So X confusable, but not Y confusable. And so the main result is the following. Suppose P of XY is X confusable, then any scheme operating at a rate R1 less than H of X satisfies local probability, which cannot decrease, which is tied to the to locality. Okay, so it's not a non-exponentially decaying in N, it is weak locality. Okay. And the other thing to notice is that this is irrespectively of R2. Okay, so even if the receiver has full knowledge about Y, Yn, if some genie comes and gives the decoder Yn entirely, you still get an error probability, which is 2 to the minus theta of L. Okay. Oops. Yeah. So the goal here is, so what we want to do is to lower bound the maximum, to the optimal decoding of a decoder that has access to the entire Y sequence and the symbols that you need to read to get symbol I. Okay. Okay. So here CIIs, those are the set of symbols that I'm reading from the X archive. Okay. And I'm giving the decoder full access to Yn. Okay. So for free. Okay. So there are 3 steps. The first is through rate distortion. So since you're operating below H of X, there must be errors. Okay, so this is the first inequality. And what this says, essentially, this says that there exists at least some, some particular sample of CII and some realization of XI for which, those 2 inequalities hold. Okay, and really, I mean, this is like tiny manipulation. It's essentially a direct consequence. Okay. So there exists 2, essentially this is an average, so there must exist realizations of both the symbol that you want to decode and the symbols that we're querying to decode Xi, and they should satisfy those 2 inequalities. Okay, so this is number 1. Now, number 2. Remember, the goal is to lower bound this error probability here. Okay, I mean actually the whole thing, right? So if I want to lower bound this, and I'm summing this part over C, I get exactly this, right? Just marginalize. So now we're going to use a trick to actually get rid of Yn. Okay, right? Because you're giving the decoder access to this and Yn. I don't know what to do with it. Okay. So here's one thing that one can do is to imagine that we add an X tilde here, right? So X tilde and Y have exactly the same distribution as X and Y. Okay. So there's a coupling, okay, between X and X tilde. So now X, Y, and X tilde form a Markov chain, right? So condition Y, given Y, X and X tilde are independent, and from Y you see essentially 2 identical copies, right? X and X prime, and X and X tilde. Okay, so once we introduce once we have this coupling, what we can show, and again it's a small calculation, you can show that you can lower bound this part here by a probability that does no longer depend on Y, okay, but depends essentially, that depend only on the 2 extremes of this Markov chain, okay? Yeah. So, and now we use the third trick, but not a trick, it's a very, very useful inequality, which is a hypercontractivity inequality. So because P of xy is x confusable, because P of xy is x confusable, P of x tilde y is also confusable just by symmetry. So it's exactly the same thing, right? P of xy and P of x tilde y is the same thing. So if one is confusable, the other one is also confusable, and vice versa. And as a consequence, P of x tilde has full support. Now, if I have a board here, okay, it's very simple to see, right? If you have one, two, whatever those. Yeah, okay. So this is for x. This is for x. This is alphabet y. So this is x tilde, and this is y. Okay. So let me draw I'm drawing an edge between any pair of samples that have a positive probability. Okay. So by symmetry, I should have exactly the same thing, right? So I should have this. I mean, maybe this one goes here. Okay, you understand, right? So this is whatever. Whoops. I'm missing something here. Yeah, this one. Okay. Okay. So what I'm claiming is that P of x tilde has full support. Okay. So that means that if I take any of those, for example, this one and this one, there is a path between them. Okay. So why has the probability of those pairs symbol, why is this the probability of this, well, sorry. If I take any x and x, tilde symbol, we should have there should be a path between them, right? And the reason is the following, is that if I take any pair of x symbols, right? So first of all, so this x tilde here is the same as this symbol here, right? It's identical, right? So now, I mean, because the source is x confusable, there exists a y that connects. Oops. There is a y that connects both to this symbol and this symbol, right? So by symmetry, this symbol here connects also this one and this one, right? And that's it, right? Now we have, you have the probability of x, right? You have a triple, and that's it. Okay, you have at least some mass. Okay. Okay. So again, so the conclusion is, because of P of xy is x confusable, P of x tilde has full support. And now we have this amazing inequality, which says that, I mean, it's completely general, and it basically allows us to lower bound the probability of a joint event between x and x tilde by the product of the product of the probabilities of the two and the product of the two marginals, basically. Okay, and we use this inequality, and this is how we get the final answer. Okay, so I think I'm just going to leave it there. Yeah. So again, rate distortion. Then there is this coupling that we are using to get rid of y, and then we are using the hypercontractivity inequality to lower bound the probability, and this probability here. Okay. Okay. Yeah, I think I'm so in terms of just a few concluding remarks. So one thing which I did not talk about is compression with both constant local encoding and constant local decoding. It turns out that you can ask even more than constant local decoding. You can ask for constant local decoding and constant local encoding, and there won't be any rate loss. Then there are some, many open problems here, like generalization to sources with memory. For for example, for the problem of privacy that it described, it's still unknown. We don't know whether there is a rate loss or not when the source is Markovian, for example. Okay. Now, the other thing one can consider also is other primitives. Other than encoding and decoding, like for example, search. How efficiently can you do search over a compressed string, for example? Okay, and then you can also, for example, consider compression with locality in the context of other data structures like a graph. Okay. That's inclusive.
Okay, we have time for a few questions.
Mansour.
Understand the coupling argument. If P of X is X inclusive.
Yes. So yeah, because okay, so I need to show that the probability. I need to show that the probability of any pair of symbol on the left side and the right side is positive, right? So how do I do this? I pick this one and this one, right? For example, okay? So the symbol here is the same as this one, right? So because the source is X confusable, there is a Y. Yeah, I think it's this one. There's this Y here, which sees both X and X, not tilde, X bar, I guess. Okay, which is both. Okay, but now by symmetry, this X tilde also is connected to this one, right? And so then you have for some Y, you have P of X, Y, X bar, which is positive, right? So probability that X equals X, Y equals Y, and X tilde equals to X bar. This is positive, right? And I can just sum over Y, marginalize and get what you want.
But why we should introduce X by this coupling? It's like a hidden trick.
It's a hidden trick. So we had lunch together, and I told him that there is a hidden trick, and I was asking the question. So
Trick in the trick.
it's a trick in this, yeah. So I mean, this whole you can just well, so first of all, the thing about introducing a coupling, this is not new. Okay, what is new is how we introduce it. Okay, so introducing a coupling there's nothing. I'm sorry, it's not here, right? Is oops, where is the coupling? Yeah, here. Yeah, so it's here. So one, and this is a generic. This is a generic idea. Basically, you can see and say, I don't know what Y is. Can I provide some other information that I can leverage on, and that will, that will allow me to lower down the distribution. Basically, you're trying to replace this Y by something else, okay? And introducing the coupling allows us to do that. And on top of that, we had an eye on we knew about the hypercontractivity inequality. And so we knew that, if by magic we can kind of introduce, this extra information for which we can use the hypercontractivity result, then that's how we would get it, okay?
Starts with trying to kick out Y.
Try to kick out Y, exactly. This is exactly, okay? And it really, there is no mystery. This is like a few lines calculation. It's not much. It's really like, it's a small exercise. It's not much. But yeah, the whole point is to try to replace Yn by some other information, maybe not as useful, but that would still give us a reasonable lower bound.
I had a question. I mean, I'm more used to channel coding, as you know. Do some of these concepts extend to channel coding?
Absolutely. Yes. So channel, I mean, there's a lot about, and on channel coding is much more known actually.
With this
So-
notion of locality?
Locality, yes.
Oh,
Much,
I
it is
see.
much
Okay.
more that, yes, a
I
lot.
see.
In fact, it started much early. I mean, this is like all the stuff, I mean, for data compression is all since 2015.
Mhm.
But, you know, channel coding with locality, it exists, you know, it has at least, yeah, I would say 10 years more.
10 years more.
Yes.
Okay.
Yeah.
And another question we linked also by to that. So, I mean, is there also a quantitative theory for error equivalent of error exponents when you add this notion of locality? I mean, how does it affect the
Error exponent. And
yeah.
you're asking a tough question because it's all order, you know, it's exponential decay.
Yeah.
Now, if you want to get into error exponent, it's a, I don't know. I mean, one related question is, okay, for example, in the context of privacy, so you know we can do it. Obviously, so you can ask both for privacy and locality, right? So for the moment, the number of bits that we're querying for privacy is non-local, is non-constant, is logarithmic in n. Then you can ask, can you get fewer? And then, you know, this, I mean, addressing this type of question can help, you know, down the road, try to figure out that these bounds on the error exponents. For the moment, the bounds that we have, I mean, this type of analysis would give like fairly crude bound on the error exponent. Still non-zeros. You can still show exponential decay, but yeah, more difficult, yeah.
Any other question? Okay. Please.
I'm not sure if it is long or not, this question, so you feel free not to answer. I was wondering about the privacy decoding, if it has application on data structures such as Bloom filters, because
Bloom filters,
Bloom
yes.
filters, because in that case you have membership queries, and when you insert or when you query for the membership of an item, actually some of the bits may correspond to different elements in the set.
Yes.
So while if you have privacy preserving mechanisms, it happens that this actually affects the false positive probability of this Bloom filter. But if any bits that you query for the membership is